Hi, welcome everyone. I'm Daniel Cisneros, and today I'll present regression analysis of energy efficiency for building design. The goal is to understand how architectural decisions, such as the geometry, glazing, and height, can impact heating and cooling loads in a building. This study is going to combine statistical modeling and machine learning to provide actionable insights for sustainable design. So the purpose or the main goal to do this project is that buildings consume substantial amount of energy. And if we take a look around, we can see that we have more constructions of different type of buildings that serves different purpose, such as business or residential. So with the use of statistics and machine learning, it can help us understand the energy requirements of an early architectural stage design, where we can provide data-driven insights to make informed decisions before relying on an HVAC systems, which is the AC units for big buildings. So this is going to be our outline for today's presentation, where we first are going to take a look at our dataset analysis, where we do exploratory data analysis and create plots to get better insight of our data. Then we're going to take a look at our modeling approaches, including linear regression and random forest. And very slightly, we're going to go over some regularization techniques. This is going to be followed by a model comparison where we go over different metrics for performance and error of our models. Finally, based on our findings, we're going to go over the recommendations for future insights. So let's take a first look of our dataset. This dataset comes from the UCI Energy Efficiency dataset, which has 768 samples, where we have 10 variables, where 2 of them are going to be our target variables. The 2 target variables that we're going to focus on are the heating and cooling load, which represents the annual energy requirements for heating and cooling. Then we have the orientation for building from north, east, south, and west, followed by the glazing area and glazing area distribution, which covers the window index and the percentage of floor area from 0 to 40%. Then we have the wall and roof area, which covers the exterior of the wall and the roof surface area. We also have the overall height of our buildings in meters and the surface area, which we're not going to use to avoid redundancy in our models and to reduce dimensionality. Last but not least, we have the relative compactness, which indicates the volume to surface ratio, where higher values equals more compact forms. So this is going to be our correlation heat map, where we have some strong positive and negative correlation and a minimal correlation, or which means no influence in our models. So from this we can see that the overall height has the strongest positive correlation, followed by the relative compactness from our target variables, which we can see the heating and cooling load. Then we also have a slightly positive correlation for the wall area. Then for the strong negative correlation, we have the roof area against our target variables. And then after that, we can see the gray boxes, which means the minimal influence or almost no influence in our models, that we're going to take a look at this with further explanation. So we have orientation, the slightly glazing area, and the glazing area distribution. So let's take a look at the box plots for orientation analysis and the glazing area. First, we're going to focus on the left section, where we have the orientation for heating and cooling loads. So by taking a look at the orientation for each model, we can see that all of the box plots looks almost identical to each other. Especially when we look at the median for each orientation, we see that there's no difference in them. So based on this information, we can drop this feature since it won't impact the performance of our model and we won't gain much information from it. And this will also help us to reduce dimensionality. Now, if we took a look at the glazing area, we can see a totally opposite effect where we can see like an upward trend for each of the box plots and where we have a different percentage of the glazing area. So less area means cooler buildings and more glazing equals to higher load. So we can see a totally opposite effect from the orientation, which means this feature is going to have a strong influence in our model. After we have a better understanding of our data, we can use this to create linear regression to fit our model. And this is the result that we get. So first let's take a look at the heating load from the left part. So we can see that we have a very strong R square, which means that the model explains a 91%, where on the cooling load we have a slightly different R square, but it's still pretty strong. Both of our models are statistically significant. So now let's take a look at the variables, and we can see that for both models, most of the variables are statistically significant, except for the cooling load, where we have the glazing area, which is not statistically significant. But before we go deeper into that, I would like to talk about the residuals diagnostics for both models, where we can see or we find out that both of our models have non-normal or deviate from normal. So having to rely on the p-values are not trustworthy. So we have to do additional analysis to confirm of our insights. So let's take a further look at our regression diagnostics using QQ plots and the residual versus fitted analysis, plotting the lowest curve. So first let's take a look at the QQ plots from the left. And we can see that for the heating and cooling, so for the heating load, we have some left skewness, and for the cooling, we have some moderate right skewness. This not really deviate a lot from the normal, but we have to take this into current consideration. And then we have the residual versus fitted. So for the fitted plot, we want to see the random scatter of points around zero, and we can see that we have some patterns which is not ideal for our model. And by taking a look at the lowest smoothing, it again suggests non-linear. So now we can proceed with random forest. Why random forest? Because with this model, you can capture non-linear interactions, which is the main problem that we're having with linear regression. But linear regression is an easier model to interpret and to understand what's actually going on. So now let's take a look at the random forest feature importance for cooling and for heating and cooling. And we can see that for both models, relative compactness ranks first as the most strongest predictor. Then we have the height and roof area, which are also significant features. But at the end of our models, we can see that the glazing area distribution has no impact in our model. Now let's compare the actual versus predicted for random forest versus linear regression. So first let's take a look at the random forest, and we could see random forest performs really well when it comes to predicting our data points, with most of the data points being on the red line, Where on the linear regression we can see some data points scattered around the prediction line, but it's not as good as the random forest. Now, a similar case we have for the cooling load, where random forest performs better than the linear regression. So we can see that random forest actually captures nonlinear patterns, which is better than linear regression, resulting in a more accurate prediction for both heating and cooling loads. So now let's compare the model performance of between all of our models with metrics for the R square, the mean absolute error or MAE, which is the average size of the prediction error, and the root mean square error or RMSE, which also measures errors but is slightly more strict when it comes to penalizing these mistakes. A quick summary of this slide is that random forest outperforms all the models in all metrics, but let's take a deeper look at our graphs. But first, why use regularization techniques or methods like Rich and Lasso? This is because Rich and Lasso models shrink coefficients, reducing variance and stabilizing the model. This makes the linear approach less sensitive to collinearity, and which is a common issue in architectural datasets. Now let's take a look at the R square with the where higher the value, the better. So first we have the random forest, which we can see outperforms all of the models for linear regression, lasso, and Rich. For this metric, the higher the better. Then we have the MAE comparison between our models. And then we can see random forest performed the best because the lower the value or the lower the error, the best our model is going to perform. And finally, we have the RMSE comparison, which again, the lowest the value, the better for our model. And we can see again random forest being the lowest, having the lowest score for all of the metrics and models. So despite using regularization models which show some slightly improvements along with linear regression, let's remember that um, this regularization shows some improvement but still fail to when it comes to non-linear data. So even though these models have a strong R-square predictors, they still violate some core assumptions for linear regression. So for this one, random forest is going to be the best models to provide insights of future models designs. So to summarize this presentation based on our insights and data, here we're going to have a hierarchy of design influence where the most important is going to be the geometry of a building, specifically compact forms reduce surface area to volume ratio. Then we have the envelope exposure for wall and roof areas variables, which impact heat and cooling transfer. For glazing area, a moderate 25% or lower suggests a balance between efficiency. Finally, uh, when for the orientation of the building, it seems to have no impact of the model. Therefore, the recommendation for future buildings is to favor compact forms, limit glazing proportions, avoid excessive heights, and use machine learning for early state design before relying on HVAC systems. And of course, as previously shown, three models that can capture nonlinear interactions is going to be our best approach. So this is going to be the end of our presentation for today. So please, if you have any questions, just let me know. You can write me an email or just contact me through any forms that you feel better. and thank you for your time.